Before we consider probability density functions, or PDFs, with continuous data, let's just take a step back for a moment and look at the example that we considered already with discrete data. This was that example where we tossed 4 coins, or 1 coin 4 times, and we had a look at the number of heads that we expected to get. And it could be anything from 0, 1, 2, 3, up to 4. Now, the probability density function, well, it's not really a function when you're working with discrete data. We called it one to ease our transition into the continuous data. Really, this is a probability density histogram, and the orange line is its associated polygon. And over here we have a cumulative probability density histogram with its associated polygon. Now you can see that the scale on the vertical axis is quite different for each. Here we only needed to go up to 3/8 because that was the most likely thing that would happen, getting 2 heads. Whereas over here our scale goes all the way up to 1, and that's because by definition our cumulative probability density histogram needs to include everything right up to a certainty, because by the time that we get up here we're saying the chance of getting 4 heads or less must be 1. So these are our probabilities between 0 and 1, whereas over here we just have probabilities up to the highest one that we're expecting. Now, a few little things to notice. We've already mentioned that the area underneath this polygon is 1, and that's important as a concept when we get down to looking at the continuous data. But we also can see a few other things. If we look at the probability of getting 2 heads, we can see that half of the data is on each side. So clearly that's halfway through the probability distribution. And we've just learned how to look at CDFs, which this is one of, and say, how do we find the midpoint? So if we look at the probability of a half and see where it lines up, it actually comes across here and hits our graph right at 2, which makes a lot of sense with a symmetrical distribution like this one. So if we now take our understanding with the discrete data and look at drawing the PDF and the CDF with continuous data, we can use our example that we've just seen with the chook wandering around its circular yard. But there's 2 problems. The first problem is that we've got an infinite number of columns on our histogram, so we can't actually draw the histogram. We can draw the polygon, and that gets us around that. Instead of having a jerky orange line like we have here, we'll have smooth lines, and we're calling them functions now because that's the terminology that we use for these smooth lines that sit on a vertical and horizontal axis, or a Cartesian plane. The second problem that we have, though, is that this chart tells us what the exact probability is of any one outcome, whereas this one tells us the probability of getting that outcome or less. Okay. Now we can do that just fine here, but the problem is we've already considered, and I've written it down here, we can never find the probability of our random variable taking any one value when we're working with continuous data, because the probability of getting any single value is actually 0, and that's because by definition there's an infinite number of values. So we've already seen that we get around that by looking for a range of values. Now I've put a little teaser in here of what we're going to do. We're going to integrate. Now why are we integrating? Well, let's consider how we made this table from this one. Now obviously these scales are a little bit different, but if I gave this histogram the same scale as this one, it just means that it would spread up a little bit taller. I've virtually taken each of these columns and stacked them on top of each other, so that this one is the height of those 2 together, that one is the height of these 3 put together, this one is the height of all those 4 put together, and this one is the height of all of them put together. And that explains why it's 1, because all of these probabilities add up to 1. So with discrete data we can add the columns together, but the whole concept of adding infinitely thin columns together should be familiar to you. That is the basic definition of integration, or the basic theorem of calculus. So we can go ahead and reason then that we can integrate this function to find this one. So you'll see the terminology here, and you might have wondered already, why have we been using this capital F of x? If we're talking about a function, why don't we just use little f of x? Well, remember when we first learnt how to differentiate. And we said if you differentiate f of x, then you can get f dash x. And then if you integrate f dash x, you get back to f of x. So we have this cycle going around of differentiating and then integrating. Well, the natural question is, what happens if we start with f of x and we actually integrate that? We'd better have a name for that thing. Because otherwise, how can we integrate things multiple times? We're going to need some more terminology. We can clearly differentiate lots of times because we can get f double dash x and so on and so on. But what if we go this way? And remember, we came up with this and we said the primitive of little f of x is big F of x. We called that the primitive. And we learned already in year 11, in year 12, the start of year 12, that to integrate a function of x, we'd get big F of x. After a little while, we didn't use that so often because it seemed a bit clunky, and we preferred just to say if f dash x equals this, and we integrate it, find f of x. But this is the same sort of process. So clearly, we can differentiate this to get here, and we can integrate that to get there. Now, the one that we can figure out with the point chook is the probability that the chook is anywhere less than a certain radius. And we already found a formula for our primitive. So then the reasonable explanation to use is that if we can integrate to get from this to this, and I've written this down here as a big picture for you to copy down, if we can integrate to get from here to here, but we don't know what this one is, we can find the formula for it by differentiating. So, nice and easy to differentiate this. Let's bring the 2 down the front. It will cancel with the 36 that's there and give us x over 18. So if we want to graph this then, I'm not going to call it the probability that big X equals X, because we really can't use that with continuous data. As a concept, it doesn't work. Let's just call it plain old f of x. And if I ask you to graph y equals x over 18, that's the same thing. Well, it's in the form y equals mx plus b, where the plus b is just nothing, so there's obviously no y-intercept, or the y-intercept is 0. And the gradient is 1/18th, because we can write this as 1/18th x, and it means the same thing. So I've got a straight line. Now, I knew that my chook could be anywhere from 0 to 6 metres away from the centre, so it makes sense to put my 6 on there. I know I've got a straight line that starts at the origin, so I can just graph in any line here. And now to lock in my scale and make it make sense, let's just sub in when x equals 6, f of x equals, and we can see it's 6 over 18, which is the same thing as 1/3, so we've put that up there. Now, another thing you should be noticing is that if this really was a parabola, which we knew that it was, it makes sense that when we differentiate it, anything to the power of 2 is going to drop down to something to the power of 1, so I can see that it's going to have that form of a straight line. Now, how are we going to use this straight line or this function? We've already said we can't use it to find individual points, okay? So we can use it for a range. So now we have a little formula. We can find the probability that x lies between any two bounds, a and b, by just finding the definite integral of f of x between those bounds. Now with the example with the chook, we could actually use this rationale here to solve a whole heap of problems. Remember, we found the probability that the chook was between, 2 and 5 metres from the centre, and we found that by finding big F of 5 minus big F of 2. And that made plenty of sense, and we were able to solve it. Well, this formula is giving us a very similar method to do the same thing. And one of these methods might just sit more comfortably in your mind. We need to understand them both so we can see how they fit together. We could also solve this problem by saying we need to find the definite integral between 2 and 5 of f of x. Now, if we've got f of x and we know it's this, we'll put x over 18 dx. Our next step would then be to integrate that, because perhaps we've started with the PDF and we need to integrate it to get the CDF. Other times we might start with the CDF and we can differentiate it to get the PDF. But if we've started with this one, then we could just go ahead and integrate it, put it between our bounds. Now if we integrate this, we need to raise x to x squared, 1 power higher. We need to divide by the new power, that's 2, and we also need to keep the constant there. So we have x squared over 36, which lo and behold is the correct integration. I can tell because we already have that. And then I just need to sub in the 5 for x and subtract the subbing in of the 2, which is the same method that we used before. So I'd end up with 25 36ths minus 4 36ths. And I get the same answer that I got last time, 21 36ths or 7 12ths. So now I've got a formal way of setting this out. And to understand what that looks like on our PDF, well, here's 6, let's say 2 is here and 5 is there. What we've actually just found then is the definite integral. We've found the area of this section, and we've found that it's 7 12ths, which makes quite a lot of sense if you assume that the entire area has to be 1. Now let's just double check that our area really was 1. That's a handy thing to check, just to make sure you've drawn your PDF correctly. Because if the area underneath from the lower bound to the upper bound doesn't equal 1, you've got a problem. Well, we've got a huge triangle, so if we just use half times base times height, the base is 6 and the height is 1/3. Half of a third is 1/6, and 1/6 of 6 is 1. So sure enough, the area underneath this entire function equals 1.